Our next topic is camphor. Camphor is a natural terpenoid, specifically a monoterpenoid ketone, known for its strong penetrating aroma and cooling effect. Here's the structure of camphor. It is found naturally in the wood of the camphor tree, Cinnamomum camphora. Here's the botanical name, and is also produced synthetically from turpentine oil. It grows mostly in Japan and Brazil. It occurs in both S and R form. The IUPAC name of camphor is 177 trimethyl bicyclo 221 heptane 2-one. Here's the numbering of camphor. Molecular formula is C10H16O. The molecular weight is 152.23 gram per mole, and the appearance is white crystalline solid, having a odor strong, aromatic, and menthol-like. Slightly soluble in water, soluble in alcohol, ether, and chloroform because it is a non-polar. Its melting point is 175 centigrade and boiling point 204 centigrade. Natural resources: camphor tree Cinnamomum camphora, native to Asia. Other sources of camphor is rosemary, sage, and some other aromatic plants. It is also produced synthetically from alpha-pinene, derived from turpentine oil. Camphor is a bicyclic monoterpenoid ketone. As you have seen in our last slide, the structure of the compound camphor derived from isoprene units. It contains a ketone group and has a rigid cage-like structure which contributes to its stability and volatility. Camphor also has uses and application. It is used for topical analgesics, relief of pain and inflammation, used in balm like Vicks Tiger Balm. It is also used for cough suppressant and decongestant, used in vapor up and inhalants. Anti-itch and skin irritation relief, used in the cream for rashes, insects, bites, and eczema. Uh, Antiseptic and antimicrobial. It is mildly effective in preventing infections. Cultural and religious uses commonly used in Hindu rituals and Buddhist ceremonies, used in aromatherapy for calming and purifying effects. It is also used in plastics, varnishes, fireworks, and as a plasticizer for cellulose nitrate. Historically, it is used as a moth repellent. Camphor also has a pharmacological properties used for antimicrobial, active against certain bacteria and fungi. Um, Anti-inflammatory, reduces swelling and pain when applied externally. Also has a cooling sensation, activates skin's cold receptors, giving a fresh feel. Camphor also used for the respiratory relief, helps clear nasal congestion when inhaled. Further, the structure elucidation: camphor added a molecule of hydroxylamine. Here you can see that when added hydroxylamine in the camphor, then there is a formation of oxime. Also with semicarbazide, hydrochloride, and phenyl hydrazine hydrochloride, uh, it afforded a semicarbazone and phenyl hydrazone respectively, to indicate the presence of a carbonyl group. It did not react with bromine or nitrosyl chloride, which infers the absence of double bond. There is no double bond present in a camphor. Thus, it was deduced that camphor is a saturated ketone. It is a bicyclic saturated ketone compound. And the presence of carbonyl group was further confirmed by the treatment of camphor with iodine when carvacrol, here is a compound, was obtained after the treatment with the iodine to a camphor. This also suggests that phenolic group has arisen from the carbonyl group, which must be in a position to methyl group in a six-membered ring. The presence of six-membered ring was spotted when camphor was distilled with zinc chloride and PCl5 to afford paracymene. Here you can see the formation of paracymene when camphor treated with the zinc chloride and pentachlorophosphorus. Reaction of camphor with amyl nitrile and HCl, or we can use a nitrous acid, resulted in an isonitroso derivative. Isonitroso derivative is to reveal the presence of methylene group to the carbonyl group, mean adjacent to the carbonyl group. Hydrolysis of iso, further the hydrolysis, here you can see that isonitroso compound gave a camphor quinone which supported the presence of methylene group in opposition to the carbonyl group. Formation of benzalidine, here is a benzalidine derivative on treatment with the camphor with benzaldehyde. Here is a camphor. When treated with benzaldehyde, benzalidine derivative will formed. Formation of monobromo derivative and the oxidation leading to a dicarboxylic acid containing the same number of carbon as in camphor proved that camphor contain an active methylene group adjacent to the carbonyl group. Here is the oxidation and the dicarboxylic acid compound are formed. Oxidative degradation, camphor on nitric acid oxidation yielded camphoric acid. Further, the oxidation here is a substitution of hydroxyl group. Further, the oxidation we will get monocarboxylic acid along with the ketone, and further oxidation we will get a compound camphoronic acid. Camphoronic acid, actually camphoric acid afforded a monoester easily to show that one of the carboxyl group is hindered. Further, it gave monobromo derivative to show that one of alpha position to the carbonyl group is substituted by methyl group. These data lead to the structure of camphoric acid, which further can explain the formation of camphoronic acid. Here is a camphoronic acid. Camphoronic acid was found out to be saturated tricarboxylic acid. Here you can see the structure with the molecular formula C9H14O6, which revealed it to be acyclic. Here is a acyclic compound, and it didn't undergo any decarboxylation under normal conditions. It was inferred that all these three carboxylic acid must be on three separate carbon atom. Here you can see that all the three carboxylic acid on three separate carbon atom are present. Distillation of camphoronic acid, here is a distillation yielded azobutyric acid. Here is a compound azobutyric acid, trimethyl succinic acid. Here is a trimethyl succinic acid and the carbon dioxide. The formation of these two acids can be explained by assigning the above mentioned structure to camphoronic acid, which was further confirmed by its synthesis. Synthesis of camphoronic acid. Here is a ethyl acetoacetate compound when treated with the sodium ethoxide and the methylation on the position of active methylene positions. So, we will get firstly mono methyl substitution. After repeat this procedure, we will get a dimethyl substituted group. Further, the Reformsky reaction, that is proceed in the presence of zinc and ethyl bromoacetate, and further adding a acid, we will get a diethyl carboxylate, and further treated with the phosphorus pentachloride to convert the hydroxyl group into a chloride group. Further, the treated with the potassium cyanide. Chloride group actually removed to form a potassium chloride, and the substitution is a cyanide. Further, the hydrolysis and acid adding, we will get a camphoronic acid. If camphoronic acid had 3 methyl group, camphoric acid and the hence camphor should have the 3 methyl group. Since camphoric acid is a monocyclic compound with the dicarboxylic acid group, it explains the formation of tricarboxylic acid. Camphoronic acid, as described above, its procedures based on the structure of camphoric acid, the correct structure of the camphor was deduced as shown and further confirmed by its total synthesis. Here is the structure of camphor. Here is a total synthesis of the camphor. Mazetyl oxide, here is a group of mazetyl oxide compound when treated with the diethyl malonate in the presence of sodium ethoxide, which act as a solvent and the base. So, we will get a compound after the Dickman reactions. We will get a cyclic compound, name is 6,6-dimethyl cyclohexane 2,4-dione 1 carboxylic esters. When treated this compound with barium hydroxide and acid hydrolysis taken place after the removal of carbon dioxide, we will get a cyclic compound with a cyclic diketone. Further, this compound treated with the sodium oxybromide and acid after the removal of tribromomethane, we will get a compound 3,3-dimethyl glutaric acid. Here is a compound. Further, the esterification, we will get ester of 3,3-dimethyl glutaric acids. Further, they are treated with the diethyl oxalate in the presence of sodium ethoxide, we will get a compound diketocamphoric esters. Further, this compound treated with the sodium metal along with the methyl iodide, then there is a substitution of the methyl group diketo of camphoric acids. Further, sodium amalgam and treated with the sodium hydroxide, we will get a dihydroxyl group, because the carbonyl group reduce in the presence of sodium amalgam to form a carbonyl to a hydroxyl group, and base its hydrolysis to form a carboxylic acid. Further treated with the hydrogen iodide, here is the elimination reaction, we will get a double bond. So, when treated with the HBr, there is a addition reaction, and after the treatment with the zinc and acetic acid, we will get a compound, that is a cis isomer called is camphoric acid. Further treated with the acetyl chloride, we will get an anhydride. Here is a compound called camphoric anhydride. Further treated with the sodium amalgam, we will get a compound alpha campholide. Here is a campholide. These camphorides actually, when treated with the potassium cyanide and acid hydrolysis, we will get a compound. Here is a cyanide and carboxylic acid terminal. After the hydrolysis, we will get a camphoric acid. Here you can see that calcium salt treatment with the heat, the removal of carbon dioxide in water, we will ultimately get a required compound, that is a camphor. If we talk about the spectral characterization, main peaks of the alkyl methyl group in the upfield regions are appeared. Two methyl group shares appeared and one appear 0.83, 0.85, 0.96 as a singlet. Also in a C13 NMR prominent of the methyl group and the carbonyl carbon peak appear downfield field side 216.98, and the methyl group appeared 9.99, 18.69, 20.70. IR also showed a prominent peaks of the carbonyl group, that is appeared 1740, and MS show the M over Z value of the compound that appeared after the fragmentation. Stereochemistry of camphor. Camphor has two dissimilar chiral center, but only one pair of enantiomer is known. This is due to the fact that only the cis form is possible. Transfusion of the gem dimethylmethylene bridge to the cyclohexane ring is impossible. Thus, only the enantiomers of the cis isomer are known. Since the gem dimethyl bridge must be cis, the cyclohexane ring must have the boat form. Usually, the structure shown on the right side is normally drawn. Camphor is a versatile monoterpenoid with a long history of medicinal, cultural, and industrial use. Its distinct aroma, therapeutic effects, and chemical stability make it valuable across many fields. While safe in moderation, proper care is necessary due to its potential toxicity in high doses. Camphor remains a shining example of nature's powerful chemistry.